All right, so now we're going to move on to the second two, the calculator questions. I had to get a little bit of stuff ready for these so that I would know the answers to a lot of them. All right, so first things first, is R continuous at t equals 5? Well, all you have to do is plug 5 into both of these things. Like all the spots, here, here, here. And if you do that, what you find out is that R is indeed not continuous. In fact, the limit of R of t as x approaches 5 from the left side is 375, like a clean number. When you plug 5 in here, you get a 3000 over 8, which is this. And the limit as x approaches 5 from the positive side of R of t, that's in the E equation, equals some garbage like 367.879. And those don't match. So you're like, nope. And as my justification, I'm going to say don't match. All right, seems good. All right, next one. We're finding the average rate at which water is draining from the tank from 0 to 8. So all we have to do here is integral divided by width from 0 to 8. So we're dividing by 8. But the janky part about this is we have two different integrals. We have the integral from 0 to 5 of the nice function, 600t over t plus 3 dt. And then we add to this the integral from 5 to 8 of 1000 e to the negative 0.2t dt. And then we divide these two integrals by 8, and you should get 258.053. Oh yeah, just a quick note. I'm 2 answers in here, and they've both been pretty janky calculatory things. Kind of. You could have done this first one without a calculator. But you can see the answer key. This is off the 2011 B tests, so you can just Google that, or you can Google, like, honestly, the first 10 words of this, and you may have found it from there. All right. Find r prime of 3. So we're obviously using the first equation, because that's when t equals 3 is in that first interval. And all you do is do the derivative at a point on your calculator. Menu, calculus, and I think it's the first one in the list. And you do that and you plug in 3 with 600t over t plus 3. I'm not even going to find the derivative because you should use your calculator to do it. When you do that, you get the answer 50. And then, using correct units, we have to explain the meaning of this. So R is the rate at which water is draining out. So the change in rate is the change. It's exactly that. So using correct units, we're liters per hour squared, because liters per hour is what R of t is, and we've done it again. Taking the derivative again, divided by another hour. So 50 liters per hour squared is the change in the rate of water leaking out of the tank. Sweet. All right, last one. Write but do not solve an equation. Figuring out where the stuff in the tank is 9,000. So we start out with 12,000. We subtract this garbage, so this R of t dt thing, and we have this time a. They give us a variable, so we're going to go from 0 to a. And we're just going to keep going with R of t dt. It's very tempting for a lot of people to split up R of t, but that's a mistake because it's a piecewise sort of thing, so we'd have to like do some sort of piecewise jank, whereas we can just refer to R of t as this whole thing. So we just leave it like that. And we want where this eventually equals 9,000. So some alternative forms of this is you could just say, hey, where this integral here equals 3,000, where the leak amount is 3,000, and that would also work here. You could also say negative of this equals negative 3,000. Like, you can solve this equation further, but this equation is good enough. All right, that's 2011 B's, dude. Again, these questions are not super horrible. They do require you to know your calculator, but makes sense that would be on your final. One question. And this one ended up being very similar, so hopefully you have a pretty good idea of what's coming at you based on what's in these questions. All right, so for our first one, it says, what is the distance between the road and the edge of the water at the end of the storm? So we have a storm. The water was originally 35 meters away, and it like sneaks in because it's washing away sand from the beach. So what we do is we take the original 35 and we add what our new function is going to do to it during the storm that lasts 5 hours. So 0 to 5 of f of t dt. That's it. So you can plug this in. Use a calculator. You just plug in this dude right here. I could have plugged that into my integral, or I can just call it f of t. It does not matter. But when you do this, you should get 26.495, because this integral ends up being negative 8.505 ish, rounded to 3. All right, next, using correct units. Weird correlation to the previous problem. Interpret the value of f prime of 4 equals 1.007. So what we're looking at is f prime. So f is already the rate at which the distance is changing. That's why we had to integrate it to actually find how far we changed. So f prime is actually the rate at which the distance is changing. So it's the rate of the rate. So in this case, we have 1.007 meters per hour squared is the rate so the rate at which the distance of the rodent changing, that's f. So it's the rate of the distance from the road to the edge of the water is changing. These have had some pretty janky explanations, because, you know, it's a change in a rate. It's like the rate at which the rate is increasing or decreasing would be a pretty good way of describing this. You have some options and flexibility there. It's like, get the units right and describe the right thing. Now, and take the hints in the problem, like when they give you units, like they do in here, they say the rate at which the distance between the road and the edge of the water has been changing. Like, just add a rate to it. The rate at which the rate at the yeah. All right. Let's wipe this and do C and D. So A and B we solved. Let's wipe. Move this up and do C and D. All right, at which time during the first 5 hours of the storm was the distance between the road and the edge of the water decreasing most rapidly? So what we want is the minimum, so we want where the f function ends up being 0, because that will give us our maxes and mins in the rate graph, which we want those because we want where the rate is at a maximum or a minimum. In this case, a minimum, like a most negative rate. And so you just find those points. They are 0.662-ish or 0.6619 or, you know, that sort of thing. And 2.8404-ish. These are the critical points of that guy. Again, graphed on a calculator. Just find them. Then, because we're doing absolute extrema, similar to the way we've done so far, we got to chuck the endpoints on there, 0 and 5, and then just find all these values. So at 0, we're at -2. That's our rate. We're at -1.3976. We're at -2.2696. And we're at -0.4803. So we can see from this that the storm magnifies in power and then kind of drops off here. And we can see that the biggest rate happens here at 2.8404 hours after the start of the storm. So at what time? It's this time. So the we'd have to say the time where the shoreline is shrinking, or shoreline is shrinking the most. Is that the right way of putting it? The distance is shrinking the most. Is 2.840 hours into the storm. Sick. Wow, that says storm. Holy smokes. All right. Last one. After the storm, a machine pumps some stuff back. So the elegant way in which the answer key did this, the 2009B, that's this one, answer key did this, is what they did was they just said, hey, the storm knocks some junk out. So 0 to 5 of f of t dt, we solved that in A. It was like 8.505 or something like that. That distance is negative 8.505. So if we make that thing positive by throwing a negative out in front of this, we want that to be equal to our integral from 0 to who the heck knows what, some amount of time, of g of p dp. The variable you choose here really does not matter because they did not define what days are. So if you just say x is in days, then you're good to go. And that's all you have to have is that integral. Saying that this negative thing that pumped out during the storm, you just got to pump that back in with this 0 to x of g of p dp thing. And there are other ways to do this. You could say 35 minus this we want to be equal to g of p dp plus 35 and subtract stuff off both sides and you get the exact same thing as this. Or 35 minus or plus the integral from 0 to 5 of f of t dt plus the integral from 0 to x of g of p dp equals 0 or something, or equals 35 again, or I mean, you have so many options for how to do this, as long as if you boil those down, you end up getting back to this integral. And so if I had to sum everything up, in these problems, these comparison rate problems, you're going to be building integrals. You're going to be doing absolute or relative extrema sort of things. We did absolute in this problem. You're going to have to explain what units mean. Some of you, this is really easy for, some of you not so much. And lastly, you're going to have to do something with a rate going in and out, like the escalator problem on the most recent AP test, and account for the different rates in that. And that's it. So hopefully this has been helpful. If it was just helpful to see which years the AP tests were on so you could go look at the answer keys, that's fine too. And thanks for watching.